There we go. The recording has started. Welcome everyone to our Nano Future, from discovery to innovation, presented by Maytech Networks. I'm very pleased to have with us today Celia Merzbacher, who's the VP for Innovative Partnerships at the Semiconductor Research Corporation. And there's my picture on the lower right of the screen. I'm your host today, Mike Losecki at Maytech at the Maricopa Community Colleges. Now, before I introduce Celia, let me tell you the objective of today's presentation. First, we'd like to introduce nanotechnology in its current and promising applications. Objective 2, we're going to take an in-depth look at nanoelectronics and more complex nanomaterials. Really delve in a little bit into that area. Number 3, we're going to give a perspective on future directions and emerging trends. And finally, depending on time, we'll have an opportunity to address issues and implications for education, the workforce, and policies as well that drive this emerging industry. Celia, welcome very much today. I'd like to introduce you as primarily responsible for developing novel partnerships at the Semiconductor Research Corporation. And I know you deal a lot with government stakeholders as well as the private sectors. Would you like to tell us a little bit more about yourself?
Well, thank you very much, Mike. It's great to be with you today. I'm in Washington, D.C., and I'm in a room that may have some background noise, so I'll apologize up front if that interferes, but hopefully it won't. I am with the Semiconductor Research Corporation currently, but I show on this slide a little bit of my background that I thought you might find interesting and relevant to the presentation today, because I really started out as a materials scientist and a nanomaterials scientist with the Navy at the Naval Research Laboratory. I went from working at the bench in materials to in the Office for Technology Transfer, and had a chance to learn something about that phase of innovation, that is taking research results to those who can actually commercialize and make beneficial applications of the research. So that's a very exciting part of the whole process. And after that position, I had the opportunity to work in the world of policy, and at sort of really high levels. I was still with the government. I was overseeing the National Nanotechnology Initiative as it grew from a very young and small program to the more than $1 billion program that it is today, involving 25 or 26 federal agencies. So I have that sort of perspective of the research world from the government side, and then left government to go to the private sector and work with an industry consortium, SRC, that is investing in university research on behalf of its members in the area of semiconductor research, which, as I'll talk about a little bit later, is really nanotechnology in action today. So that gives you a little bit of background about who I am and my credentials, hopefully, for talking about nanotechnology and its potential for the future. I think I have control if I go forward now. I'd like to know a little bit more about you. So I think we have a poll slide up, and folks can use their tools to respond to that.
Thank you, Celia. For those of you online, notice where the polling box is. This graphic shows you that's the fourth box right on the participant area, and please choose A, B, C, D, or E, whether you're involved with K-12, at a four-year, a government agency, and so on. So please make your choices. I'm going to make mine. Let's see which is mine right here. Okay. So let's give you another 4 or 5 seconds to take a look. Let's count down. 5, 4, 3, 2, 1. Shannon, let's go ahead and close the poll and show the results. And there we'll reposition the poll. So you've got quite a spectrum of people here today, Celia.
Well, and maybe we missed a category that was important, or I guess some people didn't vote. That's what.
Right. No problem there.
Okay, great. Well, so it looks like most folks are with higher education. and that's very good to know. Hopefully some of the material that we cover today might be of use to you, and I hope folks will use the chat window to ask questions along the way.
Good.
So we'll launch right into it, and I have included some pretty basic stuff here at the beginning. I think it's going to be familiar to most people on the call, but I just want to make sure we're all on the same page. And so I have a couple of sort of definitions about nanotechnology up front here. What is nanotechnology? And I think this might be a quote of Richard Smalley. It's about understanding and using stuff. And I put that word on purpose because it's really about material, but it's about using material. And then the other piece that's important is this size range, 1 to 100 nanometers in size. And it's not smaller than 100 nanometers. It does have a lower boundary of 1 nanometer because it's not intended to include sort of subatomic physics. It's about stuff, and stuff has to be a certain size, but nano stuff is small. So it's 1 to 100 nanometers, and I just had a shot from the nano.gov website on this slide, which has a lot of useful information. So if you or your students are trying to get up to speed on nanotechnology, this is a great resource, and it has this tab called Nanotechnology 101 where you can learn a lot of basic information and good background material. So I think I have another question just to keep folks thinking about this and to sort of refresh your memory. How small is a nanometer? And this is really about scale, which is, I think as an educator, especially of younger age students, is hard to communicate how small a nanometer really is. So this is a question that's intended to get you to think about the difference between a nanometer and a meter. So as I think we all know, a nanometer is 1/billionth of a meter. So if you were to sort of scale that up and a nanometer was now the size of a marble, how big would a meter be if you scaled it up by the same amount?
This is a harder question. This is harder than the first one.
Well, it is, and it sort of, I think, goes to the point that we all have reference frames, and we think about things relatively all the time, but this really challenges you to think about what the factor of a billion means. So are we opening the poll now?
Yes, the poll's open, so participants please answer A, B, C, or D. Make your best guesses. Use the box. I'm going to give you, people are rapidly calculating on the back of their napkins, Celia. So let's give them another 5 seconds. Make your guesses. 5, 4, 3, 2, 1. Let's close the poll and take a look.
Oh,
there it is. So we got A, B, and a D, and a couple of D's in there.
And the correct answer is, in fact, B, the size of the Earth. So that's, I think, a useful thing to bring into the discussion when you're introducing this subject. And there are probably a lot of other ways to talk about scale as well.
Very good.
So we'll go on. Just sort of flipping it around now, if you have some feeling that a nanometer is really tiny, then how many nanometers does it take to make something? In this case, the thickness of a piece of newspaper, for example. So why don't we run through this poll as well? Is it A, B, C, or D? How thick is a piece of newspaper?
Oh shoot, I've got to worry about my negative exponents here. Okay, I'm doing my calculations. I'm going to make my guess, Celia. Everyone else, please make your estimates here. Okay. We're just going to give you another moment. You can use this with your students. I like these two polls of sort of getting your students working with size and scale. That's a big issue, isn't it?
Yep.
Okay, 5, 4, 3, 2, 1. Let's go ahead and close the poll and see the results. Majority for C.
Yep, and that's the right answer.
Okay.
So the crowdsourcing worked in this case.
Very good.
Congratulations,
Good.
team. Okay, so now that we're sort of in the right framework in terms of size, I'll spend a little bit of time giving you just a background of the whole field of nanotechnology. And as someone who was a material scientist when this all started to emerge, I felt like I was at the leading edge in a sense. I was using tools as they became available. I was asking questions about materials at the nanoscale. And there were some key events and activities that helped move that forward. So in a sense, nanotechnology was just the next logical thing to happen in the materials science realm. And one of the tools that was absolutely critical to progress was the invention of the scanning tunneling microscope in the 1980s. I think it was developed in the early 80s, and in fact the inventors at IBM Research, Eric Bennig and Heinrich Rohr, received the Nobel Prize already in 1986. That was sort of a record at the time, I think, for the time between the invention and the Nobel Prize being awarded. But it was an incredibly important tool, and the sort of commercial version is shown there on the bottom left. There's a chamber and probe being scanned across the surface of the sample. So you could only do certain kinds of materials initially. They had to be conductive materials, but it was really an interaction between a probe and a sample. So it wasn't an interaction between something like a beam of electrons like in a scanning electron microscope. It was a sort of physical interaction between a probe and a sample, and their ability to make this probe that was so sharp at its tip that it was able to actually sense the bumps on the surface due to atoms was what was, in a sense, very novel, and for which they won their award. And so on the right you see an example of an image from an STM. That's an image of cesium atoms, and they've used some false coloring to make those red on a surface of gallium arsenide. And you can see the individual atoms. It's really like the scientist or the researcher is able to touch and feel the surface atom by atom. Now, that also was very quickly appreciated that you could sort of turn it around and use the same tool for moving atoms on the surface and positioning atoms. So all of a sudden it wasn't just about seeing and in a sense measuring the material, but you were actually controlling the material. And those are all key aspects of nanotechnology. It's the seeing, the measuring and understanding, but then also turning it around and controlling. So you get into nanomanufacturing, and the next slide talks a little bit about some of these nanoscale manufacturing capabilities that have also enabled advances. And I highlight a couple of them here. And these are examples of what I would call tools for bottoms-up manufacturing. Traditional manufacturing is more of a top-down process normally, not always, but many, many things have been made through time, going back hundreds of years, by removing material, whittling, shaping, forming, taking something that was a big block of something and making whatever it is that you want to out of it. But there's also now the capability, and this is really important for nanotechnology, to manufacture from the bottom up. So there's the technique of what's called directed self-assembly, and it's just what it sounds like. The components are self-assembling according to some laws of physics and chemistry, and perhaps guided by some kind of a patterning or roadmap to form a material or a device with nanoscale features. And there's an image there of this blue and green sort of wormy structure, which is made using copolymer material that by engineering the polymers, you can control the size of the features and the way that they come together and form two phases that have a structure. And if you do it on a surface that's patterned, you can control that structure. So this is actually of high interest to the semiconductor and the microelectronics industry. Can you actually pattern the kinds of things that you want for an integrated circuit, which is a very complex design, of course, using this directed self-assembly instead of the etching and removal type processes that are used today. Another nano manufacturing approach is stamping, essentially, imprinting. So the figure on the left shows use of a mold, and it's actually pretty easy to make molds out of some materials, and then using that mold to stamp and imprint a pattern on a, in this case, a polymer material that then retains that shape. And that can be scaled up very successfully in general, and so you could envision doing that over a relatively large area. There are challenges to scaling up manufacturing processes in every area, and nanotechnology is one of those. And so there's a lot of interest in being able to do things on roll-to-roll type processing, so you don't have to do batches and one at a time type processing. In the bottom right, I just show a picture of some, and I apologize, I broke my own rule, which is I like to always have a scale, but these little pellets that are on the order of tens of nanometers, maybe 100 nanometers across, these are made by a mold and unmolding process. That's a picture that comes from a journal article, but it's of some materials made by a company called Liquidia, which is a spin-off from the University of North Carolina. It's sort of in our backyard. That's where SRC is located. And these are, and because they have the ability to make these nano molds, and you can, anything that you can sort of pour in a liquid that then solidifies, you could make using this process. And so it's very diverse in its application. They're looking at it for everything from vaccines to other type of drug delivery applications. So that's another scalable manufacturing process. So why do we care about nanoscale things? This is a chart that I like to use to illustrate why size does matter. It affects properties, and this is just a classic example. This is certainly not new to the last 10 years or so when we've all been thinking about nanotechnology. It's showing the effect of size on the melting point of gold. And you can see that the sort of textbook value of the melting point of gold is 1337.6 degrees Kelvin. But as the size of the gold particles decreases and you move to the left, so the bottom axis, the x-axis is showing diameter of the gold nanocrystals, the melting temperature decreases, and it decreases by a lot. There are data there, these dots, and you can see that it's reduced by half even as you get down below 5 and even 2 nanometers. So we can control the properties of melting temperature by controlling size. So here's another example, and it may look familiar to many of you. There are a number of color examples that are controlled by size. Colloidal gold is a classic example. But this one's a little bit more complex, and you can see all the description down below of what's in these vials. So the color is being controlled in this case by changing a number of different properties. So one of those is size, or so physical properties, physical or chemical properties I should say. So we have 3 sets of samples in terms of size. We have on the left 2 vials containing silver particles, one 80 nanometers and one 20 nanometers in size. The next 2 vials contain gold particles that are of different size, and the last 3 contain, again, silver particles, but different, for another reason, of differing size. And so you can see the effect of size in each of these sets of samples. Now, another thing that's different here is, well, I mentioned it, chemistry. Silver versus gold obviously affects color, and then within a particular chemistry you have different colors for other reasons. So we've got silver materials in some of these, and we've got gold materials in some of them. And again, you can read the footnote or the caption to see what's in each one. And then finally, shape matters. So I've only labeled the silver ones, but some of the silver particles are spherical and some are in plates. And that matters as well in terms of the visible color. And there is a natural example of this in nature. The color that appears on the wings of butterflies, for example, and I think peacock feathers, is due to shape variation. And so we have finally been able to catch up with nature and start to control shape in such a way that we can also control properties. So this is all, about, this is how nanomaterial and nanotechnology differs from just naturally occurring nanomaterials, of which there are many. Volcanic ash has nanomaterials. Clays are nanoscale materials in a sense. There are volatile materials caused by the ocean and so on that are nano-sized, but those are naturally occurring. There are nanomaterials that are byproducts of combustion, for example. So exhaust has a certain amount of nanoparticles in it. But when we talk about nanotechnology, we're really talking about engineered materials that we engineer for certain properties and for certain reasons. So I'm going to talk very briefly about some of the applications in areas that I think are of interest and could have very high impact, and one of those is for medicine. So I think there are three areas of medicine that are being impacted or are likely to be impacted by nanotechnology. First is imaging. So these quantum dots, like the ones that I showed in the previous slide, some of them, when they're made out of semiconductor materials, are ideally suited for tagging and imaging in biological systems. And so there's been a lot of interest in being able to use those. They're very bright, they're very good, strong, fluorescing materials for imaging purposes. They have some advantages and some disadvantages over existing materials, and so there's a lot of research going on in that area. Another area where nanotechnology is going to impact medicine is in diagnostics. And here I'm thinking of a variety of applications. You could have nanofluidic devices, lab on a chip sort of technology where you have the ability to characterize samples looking for certain biomarkers by the thousands on a single slide, for example, thanks to being able to make nanofluidic and nano sort of chemistry on a chip. Another application in the diagnostic space is shown over on the right-hand side, and that's a picture taken from some work done at NIST on DNA sequencing using nanopores. It's a little bit hard to see, but you can read more about it on NIST's website. They tag the sequence, the C, T, G, and A components of a DNA strand with these polymer materials that are different characteristics, and then as the chain goes through the pore, the different polymers are detectable, and there's sort of a little schematic at the bottom showing how you can gene by gene or by each unit sequence the entire segment. So that has the potential for being quite cost effective, and as they're working on making it faster, it could become really a very effective tool for doing diagnostic type work in the medical area. And then the third one, and the one that's I think most in some ways futuristic sounding, but is already I think making a lot of progress, is for therapeutics. And this is taking advantage of the idea that nanoparticles are able to be manufactured in a very controlled way and can be then customized or functionalized by decorating the surface with targeting ligands that can detect cells in the body, so they can go right to cancer cells, for example. They can really fine-tune treatment so that the side effects that are associated with a lot of medicines are reduced, and you're able to really target the cells that you want to treat and not hurt the healthy cells in the body. So there's a lot of work on this to figure out how to put the therapeutic in the nanoparticle and how to decorate it and get it to where you want in the body. This also has potential, because these particles are so small, to access areas which normal therapeutics have trouble accessing. So the blood-brain barrier is an example of a membrane that's very hard or hard to penetrate, and so these nano medicines have the potential for being able to treat things that we can't really treat today. Another area where nanotechnology could have a big impact is in the areas of energy technologies, and there's some outstanding resources on the Department of Energy's website that relate to nanotechnology and energy. Just some of the applications are shown here. Solid state lighting, which I think we all appreciate, is coming already. There are some really amazing products that are long lasting and very bright and low energy consuming. So there's a lot of efficiency associated with this, but it could be improved. And the materials from nanomaterials could really make a difference in terms of improving the efficiency of these. That goes with solar cells as well. Solar technology has been steadily improving in terms of the efficiency of the solar collectors and converters, but that could be substantially improved. The numbers are in the sort of 20% range, and if they could be made substantially higher, they would really make a big impact on their applicability. Batteries is an area that I think if you had asked somebody 15 years ago about being a battery researcher, they would have yawned and said that's pretty old school and not of great interest. But in fact, batteries are an exciting area of research, and nanomaterials are having a lot of potential application there. And just in sort of reading up about it before this talk, I found some exciting information about the progress that's being made. And so battery research is being supported much more than it was perhaps a few years ago, and there's a lot of exciting advancements. And finally, I included catalysts, which is another sort of perhaps less exciting sounding area, but is an enormously important one. Catalysts are used in the manufacture of chemicals and other materials, and use a lot of very costly components. There's ruthenium and platinum catalysts, and they're in a lot of things that we use every day, in your car, etc. So catalysts are nanostructured materials, and they're ubiquitous in a sense. They're very important. It's a big industry, and so there's a lot of economic impact of nanotechnology through their use in catalysts.
Celia,
so I think we have to pause for.
Jump in there. Yeah, I'd like to remind people that there's an opportunity now to type into the lower left window or your chat window for any questions that you might have. There was a couple of things, Celia, that I'd like to bring forward. One was a comment from a participant, and I actually didn't know this. If a gold nanoparticle is less than 2 nanometers, it essentially becomes black and is only UV transmission. I didn't know that. That's pretty cool, actually.
And that's kind of amazing when you think about it, because 2 nanometers is much smaller than the wavelength of light.
Yes.
And so there's some interesting physics there when you start talking about the interaction of light with nanomaterials, because actually light is really on the order of a couple hundred to several hundred nanometers. So there's some interesting science in there.
Yeah, well, oh shoot, I was going to say, a gold, what's the size of a gold atom? I guess about 1/10 of a nanometer, or roughly, maybe a little bit larger. So you're down to a particle that has roughly 20 gold atoms in it. So there was another question from one of the participants, and essentially it says, are some of these applications actually commercialized at this point? Obviously things like solar are, but I'm not so sure about those medical applications. Are they promising applications, or are they real? Is there any, I know that's a pretty broad question, but is there anything you would say?
I think, and I should qualify this by saying I'm not by any means an expert in nanomedicine, and there's probably good information on some of the websites that we might mention or that you're going to send out after the talk.
Right.
But I think that outside the body, well, of course, when it comes to medicine, there's a lot of checks in place to make sure that that everything is safe. And so I am pretty sure that a lot of the uses of nanomaterials inside the body is still in that kind of trial and testing phase. But that's where the diagnostics that might be in the lab on a chip for doing some of the diagnosis and uses outside the body are coming forward already. So I'm pretty sure there's the potential for some of these targeted therapies in the future, but I suspect they're still in the trial and testing phase.
Okay, cool. And there was a clarification by one of the participants. They might have gotten what I said about particles being black. Looks like they're clear except to UV light once you get below 2. So a little bit of clarification there. Let's go ahead, Celia, with the presentation, and we'll have another opportunity, in fact 2 more opportunities for people to put in questions.
Okay. So now I'm going to touch on the use of nanotechnology and electronics, and this is an area where I'm much more involved these days, and I thought I would dig down a little bit and share with you and give you a little bit more technical information as well. So electronics is really a huge area of application of technology in general, and we all rely on it more and more, it seems, because, well, we're living in a more connected world. There's this idea of the Internet of Things. Your refrigerator is online, your cell phone, of course. You know, you can get information and data about your house by logging into your computer. You can know where your kids are. You can track everything, it seems. So it's a very connected world these days. It's a more mobile one, so there's wireless communication between things. All of this means there's a lot more data. We hear this term big data, and that applies to everything from science research to you know, data being collected on your viewing habits on cable, or your you know, use of Google or whatever. So there's this huge amount of data, which presumably means more knowledge, hopefully, for somebody. And so there's a more intelligent, what IBM, I think, very cleverly coined the smarter planet. We have a more intelligent environment as a result of electronics. So down below I just show a semiconductor wafer. Today's wafers are about 12 inches in diameter. And then some of the applications. So we all have smartphones, it seems, in our pockets. And on the right I show a smart meter. So this is sort of the future of the energy use, of electricity use at least, measuring your use of electricity not just once a month when the meter reader comes by, but tracking it through the day so that maybe users can be incentivized to use energy when it's less costly, etc. So there's presumably benefits to all parties with this kind of intelligent technology. And there's a role for nanotechnology here because everything is getting smaller, and that makes new applications possible. So I think a lot of us are familiar with Moore's law. It's not a law of physics, but it is a trend that Gordon Moore, shown there in the picture, observed. He's one of the founders of Intel. Back in 1965 already, he was able to look back and see that the number of transistors put on a chip was increasing, and it was doubling about every 18 months or so. 18 to 24 months seems to be the trend, and of course as time has passed, that has continued, and that's shown here going back to about 1970. These are the various Intel products that have come out over the years, and the number of transistors per chip year by year. So this is a really amazing trend, and the industry adopted it, I would say, and it's become a sort of guidepost for the entire semiconductor industry. It's a business law for them because you probably wouldn't buy a new gadget if there wasn't one that could do more available to you, because let's face it, a lot of them work perfectly well when we get rid of them and replace them. So from a business point of view, this has really been an engine for their economic growth. And it's an amazing thing to think about. This is a log plot, so you have this order of magnitude increase on the y-axis over time. Now, there's more than one way to increase the number of transistors on a chip. You could just make the chip bigger, and then you would have the ability to make more transistors on a chip. But in fact, we've almost been doing the opposite. We've been making the transistors themselves smaller and smaller and smaller, and thereby able to put more on the chip. And this is another sort of way of looking at the same trend. And it shows, this I think came right off of Wikipedia, but it shows a lot of information. So it has now on the y-axis is the feature size of the transistor, and it shows that again over time, and different generations or nodes, as they're called in the industry, as they have come out. And then you can see these sort of background features. Well, there's two graphical representations of size sort of in the background here, or three even. So one is some biological features. There's the head of a sperm, I guess, on the left there, and a blood cell in cross-section shown for comparison. And then there's a bacterium on the bottom left. And then there are these circles, the radius of which is identifying by color the different technology nodes or different nodes on the Moore's law trend. And so you can see how much shrinkage has occurred from the blue circle that's bigger than the graphic itself down to today's generation, which is a minute dot there at 16 nanometers, 22 nanometers. So we're talking about dimensions, and this is the spacing between two transistors is sort of the way that you can think of the size of these nodes. How closely can you print things together? You have to make the things smaller, and you have to be able to do that with incredible precision and accuracy. So this is Moore's law shown in just another sort of format. So I will pose to you another question, and that is how many transistors, we showed you how many transistors go on a chip. You can kind of imagine how many chips get sold every year, but I don't know if you can do the calculations in real time. How many transistors does Intel sell annually based on their own report?
Oh, this is really hard now. I'm trying to remember what a quintillion is. Maybe that's part of the question.
So maybe we'll answer that after we get the poll.
All right, I'm going to go ahead and let's everybody make your choices. How many transistors does Intel sell annually? So go to the polling box. I'm going to make my choice. Don't look at anybody else. Make your own decisions here. Come on, everybody, put in your answers. Make a guess. If you don't know, make a guess. People are more nervous about this one. Let's give them, let's see, 6 more seconds. How many transistors does Intel sell annually? 6, 5, 4, 3, 2, 1. Okay, close the poll. Let's see what our guesses are. We're all over the place, Celia.
Well, actually, the best answer, the correct answer one, so B, all of the above. And a quintillion, 1 quintillion is a billion. So if a billion is 10 to the 9, 2 times 9 is 18. So 10 quintillion would be 10 to the 19. So those are 2 ways to do it. And I think I did the math right. I did it a couple times last night.
That's right.
But Intel has about 15% of the market, and anyhow, if you sort of divide, and you know, I use 7 billion people in the world.
That's
so
okay.
That's my ballpark estimate of how many they sell per person. I think we're at least in the right order of magnitude. So all of the above. Pretty amazing when you, and I didn't look up, there are people who compared that to the number of cells in the body and whatnot. It's a lot. It's a lot. Now, okay, what are we talking about? So let me just briefly and walk you through this, because it's kind of, again, this is like a scaling example.
Yes.
Moore's law enabled. In 1976, the best available storage was the IBM 3350, and each one of these washing machine-sized storage units had a capacity of 635 megabytes and cost $70,000 in 1976 dollars. I mean, I didn't look up how much a car cost in 1976, but this would be several car equivalents. So that was then, and now you can, well, now this is even dated. In 2006 already, you could buy an iPod 5G that had 80 gigabytes of storage. And it's pretty easy to do the math. That's 126 of those washing machines in your iPod. And if you sort of calculate $70,000 per 635 megabytes, that would be $9 million to get the equivalent storage that was in an iPod in 2006. But in, of course, 2006, you could get an iPod for $350. So this is what Moore's law has enabled. And it's really why nanotechnology is so important to this industry, because continuing this trend is really going to continue to open up opportunities and applications and new things. So this chart gives a very simple description of a semiconductor transistor. But I'm going to talk about various parts of the transistor and the materials that go into them, so I think it's worth just briefly getting everybody kind of up to speed. And I'm a material scientist, so I'm not an electrical engineer. But Basically the body, the rectangle there, and I don't know, maybe I can grab the pointer and use it.
Yeah, we're going to test it and see if we can do it.
Okay, so here's the semiconductor, the silicon body.
Click on it to point to it. There you go.
There we go. Okay. Okay, so there's the semiconductor body. You have doped material that represents the source and the drain, and those are sort of the components of the circuit that are connected by a channel, which is in between here, but the channel is only active when a voltage is applied by this gate. So the black material is the gate, and then there's a separate layer called I should get that out of the way, gate oxide layer. So this is sort of acting like a capacitor here, and when you apply voltage across it between here and here, then you get current flowing from the source to the drain. And now I'm going to talk a little bit about as this whole thing keeps getting smaller and smaller and smaller, how that puts pressure on the design and manufacture and the materials that are all nanoscale at this point in time. So can I just go back up here? Yeah. So this chart shows a lot of data for some of the features that I showed in that last chart. We have the node shown here in blue, and that is going down over time. So the axis in this case is showing year, and this is based on projections from the industry's roadmap of 2003. So I haven't found a similar chart that was created, but the industry makes a roadmap and it updates it every couple of years. So these were projections assuming that Moore's law would continue on the size of things. That's the beauty of Moore's law. If you stay on it, you know exactly how small things are going to be out into the future. Not indefinitely, but as long as you can keep shrinking things, you can project that in year X, I will be making things twice as small as I am today, for example. So here we have the nodes shown in blue, and the nodes is the separation between transistors, and because the gate is a piece of a transistor, the gate length, that bar that was across the source and drain, is getting smaller, and it's even smaller than the space between the transistors, so you see that that's some size that's smaller than the node length. And then we have the oxide thickness. So remember the gate was the bar, but then the oxide layer is just the layer thickness of the insulator that's between the gate and the body of the semiconductor. And the physical oxide thickness is projected to go down to somewhere around, well, okay, so the y-axis here, half a nanometer, right? Here's 1 nanometer. So we're well below 1 nanometer in thickness. Here's the diameter of 1 silicon atom. So we're already in the realm of thicknesses that are only a few nanometers, a few atom dimensions, I mean. Okay, so we're actually on track, even though this was predicted in 2003, thanks to Moore's law, we're marching along here. And what happens when you get oxide thickness layers that are that thin is the electrons and things can go through them. It's not thick enough to behave. This is the problem with nanotechnology. It's the benefit and it's the problem. So these materials are no longer acting like the bulk material. So how do you deal with that? Well, you have to find a better material perhaps. Now, the first thing I showed you was just a sort of schematic cartoon. This is a picture that shows actual devices, transistors in cross-section, and this is from Intel, so it's Intel products. And you can see that marching along from left to right, we have the year that the different nodes were being manufactured, and you can see 90 nanometers here and marching along to smaller and smaller dimensions. And the technology that Intel had to come up with in order to be able to keep making things at smaller scales and to improve the power consumption. Power, as I think everybody knows, is an issue because a certain amount of it it lost to heat. And as you cram more and more and more electronics into a smaller area, you get more and more heat. And so if you can use less energy to power the electronics, well, that's good from an efficiency point of view, and it's also good from not building up so much waste heat. So strained silicon was a technology that was introduced already in early 2000s in order to improve the efficiency and allow for further scaling. Then in around 2007, this technology called high-K metal gate technology. Now they're fixing this gate problem or addressing it. There was a second generation of that allowed to go down to 32 nanometers. And just recently, Intel has announced a new technology, their tri-gate transistor, which looks completely different. So now actually, and I almost added another slide to show a cartoon of a FinFET, as it's called, a fin-shaped transistor. But now, instead of just being layers and stacked on a plane, you have the gate wrapped around the channel. So what we're showing here is a channel with a gate wrapped around it. And so this is almost going into the three-dimensional space. And the idea of manufacturing something that's on the order of a few nanometers across with that kind of precision is just really remarkable. That's what the semiconductor industry is so good at, making nano-structured materials incredibly reliably across large areas. And this is something that other industries are interested in, frankly. Okay, so that's, I think, making the point that today's electronics are nanotechnology. Now, what is this high-K material, and how can we take advantage of material properties to continue scaling, perhaps? So the old materials that were used were basically silicon. It was really convenient. This is one of the beauties of silicon semiconductors. You can add a little oxygen, add a little nitrogen, change the properties a little bit, but you're doing it all on your piece of silicon. So originally, silicon oxide and silicon nitride were the materials that were being used to make the layer of the gate. And you can see here what the dielectric value of that material is, and that's just for reference. Don't worry about the units or anything. But so 3.9 is silicon dioxide, and anything that's lower than that we call a low K dielectric material, and a dielectric material is an insulator, basically. And for some applications, you want low K, you want really good insulation. In other cases, you want high K because you want to be able to allow charge to move around a little bit. So compared to silicon, I've indicated here with the red arrows, some of the materials that are being used today in order to get thinner layers that act as though they were thicker in a way. And that's by having materials that have higher K values. And the ones that are being currently used, these are in the devices you're buying today, include hafnium oxide and lanthanum oxide and other rare earth oxides which have a higher K value. Now you may look at this and say, well, why aren't we using strontium titanate, for heaven's sake? Look at that K value. But it turns out that strontium titanate is not so stable in the environment of silicon wafer manufacture. So K value is one factor, but when you're actually going to be making something, it's got to withstand high temperature in the semiconductor manufacturing process. It's got to interact with water or not. It's got to be stable in the presence of water. It's going to be coming in contact with a lot of other materials and handle all these processes. And so there are other factors as well. So today we're using some of these exotic sounding oxide materials, but we may need to, for instance, go to new types of lanthanum aluminum oxide. That seems to be a slight improvement over some of the current materials. So these are really challenging materials problems. Now, we've been focusing on the transistor part, but in order to take a transistor and apply voltage to it, get it to switch on and off, which is the 1 and 0 that you think of in the digital world, you've got to connect them with a wire, basically. And so there are these wires that we call interconnects that connect the transistors. And as transistors shrink, so do the interconnects. No surprise there. And if you thought the transistor was small, the interconnect is even smaller. And oh, by the way, you've got over 1 billion transistors. I didn't highlight it on the Moore's Law chart, but up at the top where we are today, you've got 1 billion transistors on a chip, and you're wiring those together. So, and you've got, it takes energy to move electrons through the wires. It turns out that half of the energy used in a microprocessor today, something with 1 billion transistors, 1 billion switches if you will, is going to moving information around from transistor to transistor and on and off the chip. So the interconnects are using half of the power. And that's up, and it's predicted to go up even more. It could be as much as 80%. This is sort of looking like the federal budget or something. It's like the interconnect is the entitlement program that's eating up the pie. And the pie, oh by the way, can't get any bigger. It's 200 watts. That's your power budget. And so the interconnect problem is a sort of big problem, and it's a big problem that's here today in a sense, because good old Moore's Law is going to keep crunching along, and these interconnects have got to continue to keep up. So over on the right, I show a picture of a cross-section of a chip. And what this is showing is down here at the bottom what's called M1, metal layer 1. That is the lowest level. So the transistors are kind of at the bottom of this picture, and then you put interconnects. You have to put a sort of layer that's isolating those from electric connection. So you've got an insulating layer, and then you've got a layer of metal wires that connect to the transistors, and then you have another insulating layer, and you've got another layer of metal wires, and they're connected to each other through that insulating layer via by way of vias, what's called vias, through the layers. So here we've got 7 layers of interconnects, and you have to isolate the connecting part, which is copper, from each other through another dielectric material. In this case, you want a low K dielectric material. And so the interconnect problem, all of this is shrinking year by year. So we need new conductive materials, perhaps, because the copper is running into problems as things get smaller. And we need new insulating materials to keep the interconnects keeping up with the transistors. And just as a little factoid, I could have made this into a poll question, but I'll give you the answer. The length of the interconnects end to end that are in a modern microprocessor, and a microprocessor is, like what you see when you open up your cell phone or something. That might be 3/4 of an inch across or an inch across. It has 36 miles of interconnect wiring in it. So these are tiny wires, and there are an enormous number of them in a chip. So this chart is sort of a very data-rich chart, but let's walk through it. So there sort of is a triple challenge, I call it. One is what's happening to the copper. So up here we have a picture of an interconnect in cross-section. This is sort of at the lowest layer. So this is the smallest feature connecting one transistor to another. Its dimension is on the order of 10 nanometers in width. Now it's a little hard to see. There are several layers here, but the inner core is the copper, and then there's what's called a barrier layer. It's black, I think, in this. And there's another layer out here that's less important for this discussion. So we've got to worry about the copper and the barrier. And everything's getting smaller, generation by generation. And what happens? So down here on the x-axis, we've got what's labeled as the half pitch. And you can think of that as the node number. So we're going from 90 nanometer node, that was a few years ago. We're down today in the sort of, let's see if I can get the arrow to, here we go. We're down around here today. 22 nanometer node is sort of the leading edge. And so what happens to the thickness of the interconnects and their properties? Well, the barrier thickness is going down. That's the green line shown here. And that's down in the few nanometer thickness range. Now that barrier is important because it's preventing the copper from diffusing into the silicon. So you got to have a barrier to keep the copper from messing things up. And the copper itself is shown as increasing in its resistivity, and that's because copper has it's got grains that make up the metal, and as you get smaller and smaller, you're getting more and more scattering essentially. So the resistivity of these copper wires, just because you're making the wires smaller, is increasing. And what happens when you have higher resistivity? Higher heat. So this is a problem. And oh, by the way, if you don't keep that barrier thickness getting smaller and smaller, your whole channel is going to be full of barrier and no copper. So you've got to keep thinning that barrier. And then the third thing that's on here is the interlayer dielectric, ILD, material property, the bulk dielectric constant of that interlayer dielectric that I told you about. So you've got to keep the copper layers separate from each other. And so that has hardly changed. It's gone down from around 3 to around 2. So that's a problem that we're facing. And I just included a table here that shows the properties, the K values, the dielectric value for various materials. So remember, silicon, oxide, that's sort of our starting place. That's around 3. And there's various forms of polymers that have been used and still are used today. They're a little bit better in the 2s, maybe down to the low 2s. Here's even a specific material made by DuPont. That's probably the best you're going to get with polymers. The way now I want to point out something here. Air is 1. That's sort of the floor. If you could make air gaps, that would be great. That would be the best, but it's kind of hard to build an air layer into a semiconductor structure. But what you can do is you can add pores. So you can add pores to your polymer and make something that has a value that's lower because it's averaging in air into the bulk material value. So that's a trick that's being used today. But when you start adding a lot of pores, of course, things become more fragile and not so stable, and that's not good. So again, there's trade-offs. Zero gels are another very porous material, and you can see you can get so much air into a zero gel that it actually approaches the value of air. So these are some of the research challenges to come up with new low K dielectric materials to keep the insulating properties that you want performing well. Here's another problem that people don't realize. When you run electricity through a copper wire, you move the copper atoms around a little bit. Now, it turns out it's sort of like the electricity current is dragging the copper atoms along. It turns out that that's not such a problem in a copper wire in your phone or in your house. That's a macro scale piece of metal, and a few electrons moving atoms around doesn't cause a problem. But as the wires get smaller and smaller and smaller, so that they're really on the order of a few atoms themselves, it becomes a problem. And you get what's called electromigration voids forming. And this just shows some pictures of those voids in these copper wires. They're a little hard to see, but maybe you can see one here, and there's another one here. And so these are essentially holes in the wire. Well, that's obviously not good. You're going to have a wire that stops carrying electricity at some point. And so this is a really serious problem as the copper wires get smaller and smaller. So you need to understand and try to figure out how you might minimize that. That's a good material science question. So I think this has all been by way of showing you that silicon technology, what we think of as silicon-based semiconductors, are much more complex than just silicon. And this chart nicely shows, this is something that Intel put together, shows the elements of the periodic table that were in use in the 1980s. And then as dielectric material properties started to push the limits, they introduced new materials along the way. And in the 90s, you can see there were more. And now today, there's probably more than half the periodic table being used in semiconductor manufacturing. So anybody who's interested in materials, this is a challenging and exciting set of problems, I think. And so I'll leave you with that. I think now maybe, I just wanted to kind of make a note that this does raise some interesting questions. First of all, you don't really worry too much about putting silicon dioxide into the environment. That's basically sand. or quartz. But as you're adding all of these exotic materials, do they have an effect? Are you worried about disposal of these materials? We know that there are some questions about that. And then do you have access to all of those materials as you're making billions and billions of transistors every year? Is that something that you have to worry about? Is the supply of hafnium oxide adequate? So these are interesting questions that rise as materials pressures get put on the materials of the semiconductor industry. Now, here's just yet another way of sort of expressing Moore's law, and that is how much does it cost to buy a transistor? And this chart, the x-axis only even goes up to 2002. It hasn't been updated. But since Moore's law has continued, the price has continued to plummet, and we're looking at a log plot here on the y-axis. So semiconductor, the transistor is dirt cheap, literally, these days. And so that's another factor in what nanotechnology, as these continue to get smaller, what nanotechnology is making possible. And sort of, it's hard to imagine. I think hopefully many of you can remember before the days when everybody had a phone in their pocket, and we just take this for granted almost today. So what's going to be possible thanks to this continued scaling, the continued decrease in cost of these technologies going forward? And just to sort of put it in perspective again, a microprocessor that you would have paid $1,500 for in 1986 today would cost 50 cents. And we see that, I think, in the decreasing cost of memory and memory sticks and all of the things that go with this technology. But what happens when the transistors reach their limits? So this is really the question that's facing the industry. I haven't really talked about the end of Moore's law, but we do have a limit. There is the size of the silicon atom and other atoms that we're going to run into as things continue to get smaller. And how do we, this industry has been extremely resourceful at coming up with ways to work around problems. As I mentioned, the wavelength of light is much bigger than the features that they're using lithographic processes to make today, and they've come up with very clever solutions to these challenges. I think we've reached the end of Moore's law and passed it many times. So, but there is a physical limit to how big atoms are, and you cannot make things smaller at some point. And so what will this industry do in order to continue this trend? Now there's nothing on this trend, I will point out to you, about size. It's price versus time. So if it were up to date, we'd be at some point of price in 2012. And how do we continue that trend to offer more technology for less cost going forward? That's sort of the bottom line for business. So we've got a point here where we can take questions if there are any.
It's it's really a fascinating thing. Seeing what strikes me is how complex these interacting things are. It isn't just one thing. It's such a complex nature. There's a couple of questions, but in the interest of time, I know we want to talk a little bit about implications for education and workforce. I think we're just going to forward to you one question at this point and go ahead, and then have you go ahead from there. And here's the question. I'll rephrase it a little bit. Obviously, although Moore's law could continue by continued, addressing these challenges, it's obviously going to be hugely more expensive to do so. So maybe this price per performance line won't be able to continue. Moore's law may be able to continue, but do you think the price per performance is going to maybe flatten out at some point? What's your thinking about that?
Well, I have a lot of faith in the smart engineers of these companies, and I think Moore's law is going to continue for a couple more generations. I think it takes a while, even though they come every couple of years, so it seems like they happen very quickly. There's a lot of preparation that happens. So they already have technology in the pipeline that's being sort of perfected for commercial use, and Intel has signaled we've got the next couple of steps figured out, more or less. But then question mark maybe after that.
Yes.
And I think that there are other ways kind of skinning the cat, so to speak. You could, instead of having everything being plated out in 2 dimensions and pattern, what if you did go up to 3 dimensions more, and there already are stacking of features and getting fewer interconnects by virtue of where you put the transistors, not all on one plane, for example. So going to 3 dimensions is one solution, and continuing to look at some new technologies in the nano space, which I'm going to talk about next.
Why don't you go ahead then?
Okay.
We're just a time check. We're about 20-25 minutes left to go, so think about that as you're pacing here.
Yeah, I just noted that.
You're good.
So onto the, oh, look at my little practice pencil marks on this slide, still there. That's fine. So this is about nanoelectronics beyond today's technology. And these are the kinds of questions that researchers at universities and at some of the research labs of the companies are thinking about. Are there ways that we can store information that use something other than charge? Right now we're doing everything with electrons, but maybe there are other ways to store and move information that would take less energy perhaps, or less space. And so that's a question. And are there materials that offer advantages? And I just showed some of the novel materials that I'm sure people have heard about. Nanotubes, they've been around for a while. There's a lot of excitement when they came out as for their potential use in electronics, because they are so low in terms of the resistivity, so they could solve some of those problems we were talking about with respect to copper interconnects, for example. And people have played around with trying to be able to position nanotubes, make and position them very precisely. Graphene, which is just sort of a nanotube unrolled, a single layer of carbon atoms, is a newer material, has also some interesting electronic properties that have led to a flurry of research. And so there's a lot of excitement about carbon nanoelectronics. So these are some materials that might be in the future. And this map I just used to remind me to talk a little bit about what is the industry doing in terms of this far ahead research. And this is where SRC comes in. So SRC has a number of research programs, and one of them is the Nanoelectronics Research Initiative, or NRI. And NRI is a group of companies coming together, pooling their resources to fund university research that's really long term. So our other programs are looking more at the current silicon technology. How do we stay on Moore's Law? This is really asking the question, what happens after Moore's Law ends? And we have a number of centers that are shown on this chart. And you can sort of see the different centers and the universities that are part of each one. So these are multi-university centers. They're funded by the consortium, and we're doing it in partnership with NIST and NSF. So we have some funding from the government coming into the pot, and we're also leveraging all of these NSF centers that are shown here in light blue are NSF-funded centers that are doing nanoelectronics research that we're sort of partnering with. So there's a lot of industry-government partnership in the NRI, which has been extremely beneficial, I think, to the universities because they're getting to interact with industry, to the government because they're getting to understand what industry's needs are as they go about investing in basic research, and obviously to the industry that's getting some of the best minds working on these problems. So that's a sort of overview of the NRI and the scale of it. And this just shows, and I'm not going to go through it, but you can look at it in your leisure, some of the research that's going on. And I just will point out that there's quite a bit that's going on in graphene here and there. And there's also work going on with spin-based electronics instead of charge-based. So these are areas that are getting a lot of attention and showing a lot of promise. And the industry being in the loop means that they're sort of evaluating it constantly and feeding back in their thoughts about the research direction along the way. So I'm just using as a backdrop here this picture, and I think it's fairly out of date now, of the building of a new fab, a semiconductor manufacturing facility in Chandler, Arizona by Intel. So these are enormous facilities. Ironically, the semiconductors keep getting smaller, and the facilities keep getting bigger, and it takes about $6 billion of investment to build a new fab these days. But I use that as sort of a backdrop. What are the barriers to realizing the benefits of nanotechnology writ large? And now I'm not just talking about nanoelectronics, but all of the nanotechnology applications. So we'll just discuss them rather briefly here. One is standards. When a new technology is coming into the marketplace, you want a certain number of standards, and this is always tricky about when to agree upon standards because they can be helpful and they can also be limiting. And so I think everybody's sort of familiar with the old Betamax versus VHS example of how standards helped one industry sector and not another. But nanotechnology there's a lot of variability in nanomaterials, and so you want to have customers who are buying materials knowing what they're getting, and you want people who are making and selling stuff to be meeting certain standards. So there are already some standards being put in place with respect to nanomaterials. Another important aspect of commercialization and innovation is regulation. And there are concerns about potential risks of some of the new nanomaterials, even new nanomaterials that are based on old existing materials like gold or TiO2 may have different properties at the nanoscale, as we know, so we need to understand those risks. And a small company especially may have trouble forward if it doesn't have some certainty about what the regulations are going to be. And so this is always a bit of a chicken and egg problem at the beginning of a new technology, and one that needs attention. And the government plays a role in funding some of the research there, as well as keeping an eye on things and putting appropriate regulations in place. In order for something to go from being just a gee whiz thing made in a lab to something actually useful, it generally needs to, the manufacturing of it needs to scale up. And so how do you go from these little project results to something that's actually commercialized? There's some real challenging steps sometimes for manufacturing, and that's where, as I mentioned, the semiconductor industry, with its experience in making a lot of really small things, has some lessons that it can share. And then I'll speak very briefly about the need for relevantly educated workers. And in a sense, the government's investment in research helps to educate the workforce of the future by getting students involved in leading edge research, and then they go off and work for big companies or start small ones themselves perhaps. So we need a prepared workforce, and that may involve also retraining of the existing workforce, of course. And industry is hiring. This is a picture of a fab in upstate New York from being built by Global Foundries, and that's a new fab facility. They're hiring something like 1,300 engineers and professionals, and I just put in a sort of grab off of their website, and you can go there and see the positions that are available, and you can apply online. And they're at all levels. They need PhDs, but they also need technicians and people who are going to be working in warehousing and logging materials and so on. So there's a lot of opportunities in terms of jobs, good paying jobs for graduates these days. And in fact, just last night I went onto this one website that consolidates job information and typed in nanotechnology and did a search, and I got 397 jobs that were considered relevant. And they, as you scroll through them, you see the variable requirements and the different types of companies. Here's one that's with Northrop Grumman, for example. This one with the CIA, interestingly enough. So the ones that are shown here at the top look like they require a pretty high degree. Here's one that's a postdoc at Los Alamos, but then here's one that's a secretary. Is that a nano organization? I think that's actually at a university. Over here we see the salaries, and you can see that they indicate how many have at least a certain salary range. So if you look at 70K, 115 out of 400, so about a third pay 70K or more. So these are good times for people with some experience and skills in nanotechnology. This is just sort of a familiar graphic showing the pipeline of education, and there are points along the entire way where people can graduate and get a degree and go to a job in industry or government or academia. And the whole pipeline has to be sustained, and nanotechnology is being taught, I think, at younger and younger ages. Groups in the K-12 space are learning a little bit about nanotechnology, and it's exciting and it's attracting, I think, students to study science and engineering. So that's a good thing. And I think a lot of you are part of this pipeline, and I would love to learn more about what your sort of stories and barriers are. But this is an exciting time to be in nanotechnology. There are a lot of opportunities. The government's investing in the research, and I think a lot of results are migrating out into the industry. And this chart, I think, which I was going to sort of make the end of my talk, is just showing some of the applications of nanoelectronics in particular, but we could probably come up with other neat gadgets and applications of nanomaterials in other spaces as well. And they're everything from things that are just being done today. People are using technology that's available in this case to monitor heart rate or some kind of biological information performance. And there's lots of gee whiz things like augmented reality glasses, but then you also have just the distribution, because the dirt cheap semiconductors means that technology is affordable, and people all over the world, even with limited resources, are able to take advantage of it and benefit from it. So I am prepared to either take questions. I did want to just mention that there are sort of intersections between the policy world and the advancing technology world that are kind of interesting and challenging. There are questions about regulation that come up. There are questions about what's the government's role in getting the results of this research. The government today has spent about $18 billion on nanotechnology research. How do we get, as a nation, the most value out of that? How do we benefit the entire world through our investments in research? So there's some interesting questions and challenges being posed to the future of nanotechnology, and really it's an example of an emerging technology. It's not unique. I sometimes do wonder about some of the commercialization barriers. Are they unique to nanotechnology? You can get patents on nanotechnology. The patent office is learning about nano to look at of how an emerging technology goes from a research challenge and interest to real world applications. So I'll thank you for all paying attention, and I'd be happy to take a few questions in the time we have remaining.
You know, so there's several things that have come up from the participants, and as we're doing this, I just want to remind people to put any last questions that they have, and we're also going to ask people to participate in a survey. But let me bring as we do that. So let me bring a question for you. You sort of alluded to it, but in particular, are there regulatory challenges? You mentioned regulatory challenges, particularly FDA, but what about commercial products? I mean, you know, is there a material safety data sheet for a nanomaterial, for example? I know that's sort of a strange question, but are there any particular regulatory hurdles that are unique to nano, or is it just the same as any emerging technology?
Well, I think that the answer is probably yes and no. I did sort of have to dig in on that when I was doing policy work. So just as an example, a materials safety data sheet is an interesting document. It's a sheet that's attached to a product to give information to the consumer, the customer, about the material. It's, to my knowledge, it's not a legally required document, so it's sort of best effort to share information with the consumer. And for a long time, when carbon nanotubes were sold, I believe that the material safety data sheet that was being provided was for carbon black or something like that, because it was the only carbon-based material information that was available. So there were questions asked: is this useful or not? Is it relevant or not? And when you're looking at materials such as TiO2, for example, TiO2 is being used in sunscreens, and FDA had a report, a document out called a monograph that said TiO2 has the following properties, and it's generally regarded as safe. And if you're using it in a material or a product, you don't have to do a bunch of tests on it, because we understand what TiO2 does. Well, now all of a sudden you're making TiO2 that's nanometer sized, and it may not be behaving the same in the body, and yet the FDA has a position out that it's okay to use TiO2. Do they need to revisit that? That's one example of where the size is the only thing that's changing, and there's nothing about that nano TiO2 that you would call a new chemical. It's just it's an old chemical in a smaller size. Now, there are other examples where it's pretty clear that this is a distinct phase of a material, and one of those is carbon nanotubes. A nanotube is a form of carbon that's not diamond, it's not graphite, and so the industry can say, here's our definition of a carbon nanotube, and they can clearly distinguish that, and they can identify it separately, and could be doing tests on it and whatnot. So it's a clearly distinct compound in a sense because it has a different structure. Those are two rather different cases, and so when you're asking for regulators to, they like to have bright lines and clearly definable differences. So a nanotube, they can deal with that. They can say nanotube. So it's very complicated, and FDA is putting out guidance. The regulatory process is really a trailing one in a sense. The way that regulations get made is when they're needed, and researchers are researching dozens and dozens, hundreds probably, of different kinds of materials every day, and many of them are never going to be more than a science paper, and so they don't need to be regulated or treated as something that's going to be in commercial use. And so you kind of have to wait as a regulator for something to start to emerge, and they have to be watching, and at the same time they have to understand classes of materials so that they can be smart when they decide whether or not it's something that needs attention and needs to be worried about.
Very good. You know what, let me take us through, let us get up to the survey, but to do it I just want to remind folks today that what we actually accomplished, it was amazing. And we introduced nanotechnology, talked about its current and potential applications. We overviewed nanoelectronics and really went deeper into some of those cool nanomaterials. We got a lot of perspective on future directions and emerging trends, and we really appreciated, Celia, the addressing the issues and implications for the workforce. Things have changed. There are nanotechnology specific jobs there, and you showed us that. That was pretty interesting. We're going to launch the survey right now. Celia, don't touch this, because if you or I touch it, we'll accidentally close it. So coming up in just a moment is the survey. So on your screen, you'll have a chance to click on these boxes or fill out some of the things, and it'll take just a moment for it to come up. And while that's happening, let me ask you one other question that we have that appeared in the window. And it came from a student who's working for a class assignment on nanotechnology. Where's a good starting point? Would it be the nano.gov to look at nanomaterials, or would you go somewhere a bit more specific?
The nano.gov is a great place to go for information about government programs in particular. But I think if I were wanting to dive in a bit more on some of the exciting highlights in various areas, including materials research or nano for particular applications, I might go to one of the commercial sites like the one that's called NanoWork, W-E-R-K, Nano W-E-R-K,
yes.
Or I think it's AZO Nano, A-Z-O Nano.gov or .com, and those are a couple of sites that do a really good job of tracking recent reports, and they have very user-friendly interfaces, so I think it's pretty easy to find information that's in a particular area of nanotechnology that might be of interest.
Very good.
I don't know if you know of any others.
Well, you know what? That reminds me, because on Monday, after this webinar is over, of course, but by sometime on Monday, we'll be sending out to all the participants several things. A link to the recording so that they can share it with friends or colleagues, and a a one-pager that I think has 8 of our favorite, certainly not all-inclusive, websites. And I think NanoWork, Nano4Me, that wonderful place in Pennsylvania, is on there. Several other sites that people can find technical related resources as well as education related resources. So I think that'll help too. So let me remind folks to just go ahead and complete the survey. We're only going to keep it open for another 15 seconds. So click on those buttons, type in information if you would as well. Now, I have one more question just as we're concluding. Let's look at this one. Are there groups working with SAMs, with fibers that we're aware of? What are SAMs? Who knows? I don't know what that is. Do you? Surface. We might have to ask for a clarification of what an SAM is. You think I would know that? So let's wait and see if we can get a clarification. Everyone, I'm going to close the survey on the count of 5, and then we'll be winding up for today. So 1, 2, 3, 4, 5, and that closes the survey. And thank you for participating in that. Celia, here's your contact information, and I know from talking to you that you'd welcome people who have email follow-up questions at celia.merzbacher@src.org, and there's her email on the list. Let me go through a couple of concluding slides and see if we have time to talk about self-assembled monolayers.
Monolayers.
Yeah. Okay, so today, to access this recording and slides, we're going to send you a direct link, but you could always go to maytechnetworks.org and search for this webinar and others. If you use the keywords webinar or Nano Future, this one will come up with all of its related information. To let you know, on November 16th, we have another webinar called Transitioning Adults. And that's an important focus on bridges for education. That continues that theme on November 30th. And on December 7th, Global Education and Technology. These are great opportunities for professional growth, and you can register at maytechnetworks.org. Now, if you've attended a live version of this webinar today, and only if you were here live, you can get a certificate of participation by emailing Shannon. And there you can see she's put her email address in the chat window as well. We'd like to thank Celia very much for your participation. Celia, what about that? What do you know about self-assembled monolayers? And that'll be our last question, and we've got about 60 seconds left.
Well, and I have a short answer. I don't know very much, and I think it was in particular with respect to application of monolayers on fibers, which I can imagine would be challenging because you're talking about something that's got to be coated in all directions and dimensions, and a lot of deposition processes are not very effective at that. But I can feature, if you had the right surface, chemistry, that things would bond to it, and you might be able to do that. My cells are an example of self-assembled features that can be fiber-shaped, and it's quite amazing what you can do from a bottoms-up approach.
It really is. I mean, I remember this whole bottoms-up thing. It seemed to me a lot of hand-waving years ago, but today it seems much more real. I'm fascinated by it. So. Well, we wanted to thank you again for all your participation. There was a couple of other comments which we ran out of time for, things about nanopores, and I'm sure people are able to follow up some of those things just through Googling as well. But Celia, thank you very much for the time and effort you took. It was just a great presentation, great imagery, and we look forward to working with you in the future, and thank you participants for joining in. Celia, stay on the phone for just a second. For those of you who learned how to use the emoticon, you can click on that left button, and let's give a final round of applause to our presenter. That officially ends our webinar today. Thank you. Goodbye, everyone.